Welcome to the Probability and Statistics course. In this lesson we are going to talk about two random variables and their probability function, the joint probability function as it is called. So in this lesson we are going to see what the joint probability function is for discrete random variables and for continuous random variables. Also, we are going to see how we can derive the marginal probability function from the joint probability function for discrete variables and for continuous variables. And also, we are going to give examples. So we have that, as we said, we consider two discrete random variables here, x and y, which have to be defined on the same sample space. Their joint, as it is called, probability or distribution, because we are talking for discrete random variables, function will be given by the probability of x equals x, comma, y equals y. For every x, comma, y, here we have r squared as we talk about two random variables. So what the joint probability function is, actually it is a generalization of the probability function we have seen for one random variable. For one random variable, in the discrete case, it was the probability of x equals some value x, and for two random variables, it is the probability that x and y will take at the same time some value x and y respectively. So we have that the joint probability function as the probability function for one random variable should have the property that it is greater or equal to 0 for every pair x, y in r squared. It is a probability, we expect this to be, it should be greater or equal to 0. And also the double summation, if we add up all f(x), y, the joint probability function for all values x and y, it should add up to 1. Now, the marginal probability function can be calculated from the joint probability function, the marginal probability or the marginal distribution function. We have marginal distribution function of x and marginal distribution function of y. What we actually mean by marginal distribution function, it is that we want to calculate the distribution function of x, like we had with one random variable. So from the joint, we want to calculate the distribution function of x, of only x, and of only y. That's why it is called marginal. And it can be calculated if we sum up all values of f(x), y for all values of y. So it will be a function of x. For different x, we are going to have the marginal probability function. The same way, if we actually, where x put y, we can see that we can obtain the marginal probability function of y. It is the sum for all values of x of the joint probability function. Now we have the independence of two discrete random variables. We have talked about independence of events. We have seen what it means. Now we are going to see when two random variables are independent. So we have that two discrete random variables, x and y, with joint probability function fxy, are called independent if actually their joint probability function is equal to the marginal of x multiplied by the marginal of y. Let's see an example for the discrete case. We roll two dice, and we have that by x we denote the random variable which is the maximum of the numbers on two dice. What it means is that if we roll two dice and we observe x6 and 5, the maximum will be the x6. So the random variable x will take the value 6, and so on. Random variable y will be the sum of the two numbers we have observed. We mean that if we observe a 6 and a 3, y will take the value 9. So for this example, we obtain this table which gives us the marginal, the joint distribution function for x and y. So we see here that the table has numbers here and everywhere else is 0. The joint probability function of x and y will also be 0 for all other values of x and y not included in the table. Let's understand how we have calculated this table. For example, if we take this element here, 2 over 36, what does it mean? It means that the random variable x is 3. That means the maximum of the numbers that we have observed from the two dice is 3. And also it means that we have y equals 4, that the sum of the two numbers is 4. In order to have that the sum of the two numbers is 4, we can only consider the elements 3, 1, 1, 3, and 2, 2. But because we want random variable x tells us also that the maximum from the two dice was 3, we know that one of them must have brought a 3. So we do not consider the element 2, 2, and we consider only the remaining 3, 1, and 1, 3. So we have that this probability here is actually the same as the probability of having observed the element 3, 1 or 1, 3. So this is 2 elements out of 36 from our sample space, 1 for this and 1 for this, and it's 2 out of 36. The same way we can calculate all these numbers here. Let's have a look at the 0. Why a 0 comes here? For example, we have that we have observed x is 3. X is the maximum of the numbers on the 2 dice. So the maximum number is 3, and also the sum of the 2 numbers is 9, which means that in order to have this, we should have observed on the other dice a 6. But this is impossible, as we said that the maximum that we have observed is 3. X gives us the maximum. So we know that the probability of these 2 things happening together is 0. These 2 things cannot happen at the same time. In this way, we can fill in all this table. We know that it is reasonable to let y go from 2 to 12, as we know that it is the sum of the numbers observed on the dice. So we start by 2. The smallest number we can observe is 2, is 1 and 1, 2. And the larger is 6 plus 6, 12. On the other hand, x is the maximum of the numbers on the 2 dice. So the maximum number we can observe is 1 up to 6. We note here that if we have brought 1 and 1, the maximum is 1. So if we have brought the same number on the 2 dice, we consider the one we brought as the maximum. Now, from the joint distribution function, we calculate the marginal distribution function for x and y. So we see here we have added up these lines in our table. We have that for different values of y, the marginal of y can be calculated if we add up all numbers with respect to x. So here we see, adding up these numbers for all values of x, we obtain the marginal distribution. The probability that y will be 2 is 1 over 36. The same way, we add up numbers. We see here is 2 plus 2 plus 1, 5 over 36. And so the marginal distribution function of y is given here. The same way, we can calculate the marginal distribution function of x. So the random variable x here taking different numbers. When it's 1, the probability that x equals 1 will be 1 over 36. Each one of these here should add up to 1, because the marginal distribution function, as we have already said, it is a distribution function. So it should add up to 1. And we have that here, as we can see, if we think about the experiment by itself of observing x when we're throwing a dice, that the maximum we have observed is 1, it's 1 out of 36. It's when we observe the element, the 1, 1. For x equals 2 is that the maximum will be 2. That means that we have observed a 2, 1, a 1, 2, or a 2, 2. So the probability is 3 out of 36. In this way, we can understand the marginal distribution function for random variable x and the marginal distribution function for random variable y. Now we are going to see if these two random variables are independent. We have said that in order for the two random variables to be independent, we have to have that f of xy, the joint distribution function, should be equal to, if we multiply the marginal of x with the marginal of y. Let's have a look at our table to see if this happens. So here, let's take, for example, the f2, 2. We see that it's 0, where the marginal at f2 is 3 over 36, and the marginal for y equals 2 is 1 over 36. Let's write this down. We have that f of 2, 2 equals to 0, but f, the marginal at 2, when the random variable is 2, let's write this clearly, the marginal at 2 is equal to 3 over 36, and the marginal of y at 2 is 1 over 36. We see that if we multiply these two, is not 0, is not this, so we do not need, in this case, to check all other elements in the table. We know that the variables x and y are not independent. But in order to find that they are independent, if we have an example that it was true, we found for an element that this is true, we would have to check that it holds for every element in the table. One would not be enough, but in the case when we find that they are not independent, one element is enough to show us that the equation does not hold. So we go back to see the joint probability function of two continuous random variables this time. We have random variables x and y defined on the same sample space again, and their joint probability or joint density function of the two variables should have the properties that it should be greater or equal to 0 for every pair x, y in R squared. The integral, the double integral on both variables of f, x, y should be 1. And for every area E of the plane, the probability that the pair of values, the pair of random variables x and y to be in that area is equal to the double integration of the joint probability function for all pairs in that area. And the marginal probability function, the same as in the discrete case, can be calculated from the joint distribution function. So the marginal probability function, which is actually the density function of x and the density function of y, can be calculated if we take the integral of the joint distribution function of x and y on the other variable. And the same way for y, we can calculate the marginal distribution function of y if we again take the integral of the joint distribution of the joint probability function on variable x. Again, as before, the two continuous random variables, x and y, with joint probability function f(x,y) are called independent if this holds. This is the same formula we use in the discrete case. It's just that we have to be careful when we calculate the joint probability function and the marginal ones. In the discrete case, we use summations. In the continuous case, we use integrals. Now we are going to work on a simple example to see how we calculate joint probability functions. We consider x and y two continuous random variables. And they have joint distribution function which is equal to 1 for x between 0 and 1 and y in 0 and 1 and 0 everywhere else. So this is a simple example, a simple case. We are going to draw a graph to visualize the joint probability function. We have that. Here we take x on this axis, y on this. We have x 0 to 1, y 0 to 1. So we actually have a square, the square 0, 1, 0, 1, and this function takes the value 1 for x and y in here. So we actually have the square up here, we have this area here. Now, for this example, it was a very simple example. We could visualize what the probability density function is. For more examples with two continuous random variables, it is very difficult to draw a graph to see, to have a picture of the joint distribution function. In any case, we can use the joint distribution function in order to calculate the marginal ones for x and y. We'll see in this case, we are going to calculate the marginal of x, which is equal from our formula. We have to take the joint on variable y. We know that this is 0 for any values of y outside 0 and 1. So this will be equal to, we are going to calculate the marginal of x by, we need to split our integral where f of xy becomes 0 and where it doesn't become 0. So for different values of y, we can see that some places is 0 and some it's not. So up to y equals 0, it will be 0. So we split up to 0. Then we have the area where from 0 to 1, where this is not 0. And finally, the last one from 1 to infinity. And this is equal to, this we said is 0, this is 0, and this we can evaluate. 1, this is 1 in here, and so we have that. This between 1 and 2 is 1. And so the marginal distribution function of x will be 1 when x is between 0 and 1, and will be 0 otherwise. We have that. Between 0 and 1, it's 1, and 0 everywhere else. Now we are going to see another example of a continuous random variable. We're going to calculate again marginal distribution functions, an example a little bit more complicated. So we have the times of completing two tasks are two random variables x and y with joint probability function given here for x greater than 1, then 0, y greater than 0, and 0 otherwise. Now, we would like to find the probability that the first task is completed in less than 2 hours and the second task in more than 2 hours. For this case, we actually have asked what is the probability that x is less than 2 and y is greater than 2. So it will be the double integral of x will go from 0 to 2 and y will go from 2 to infinity of this. And we evaluate this integral. Here we have from 0 to 2 as we require that the first task x is completed in less than 2 hours, so between 0 and 2 hours, and the second one that it is completed in more than 2 hours. We haven't said how long, so in theory could go to infinity. So y goes from 2 to infinity. We evaluate the double integral here, and we can find that the probability, this probability, is equal to 0.0158. Now, from the joint distribution function, we can find the marginal distribution of x in a similar way of y by calculating here the integral from minus infinity to infinity of the joint distribution function with respect to y. Here we have that this part is not, can come out of the integral as x does not depend on y, and by calculating the integral which depends on y, we can find that the marginal of f of x is equal to e to the minus x for x greater than 0 and 0 otherwise. In the same way, we can calculate the marginal of y, and we can check if x and y, the two continuous random variables, are independent. Let's see if we can calculate the marginal of y for the example we have seen, the same way as we saw before. I am just going to write the result here. Will be this for y greater or equal to 0 and 0 otherwise. I am going to rewrite here the marginal of x, so we have it in front of us, is equal to e to the minus x for x greater or equal to 0 and 0 otherwise. And we have that the joint of x and y, we remember that it was this for x and y greater or equal to 0 and 0 otherwise. And we know that, we know the marginals of x and the marginal of y, so we can see that for x and y greater or equal to 0, both, we multiply these, it is the same. If x or y is one of them, even one of them, it doesn't have both of x and y to be negative. If one of them is negative, then the joint distribution function becomes 0. Then, in the example we have, the joint probability function will be 0. So, what we have shown here is that the variables x and y for this example, the continuous variables x and y for this example are independent. We have checked for all values of x and y. As we said before, if they are independent, we have to make sure that the equation is true for all values of x and y, not for some of them. So what we have seen here is we've seen the joint probability function of two random variables, for discrete random variables, for continuous random variables. We have seen the marginal probability function, which we've said that it is actually the probability function of x and or y when we have one random variable. It is called marginal because we derive it from the joint probability function. And we've seen examples on how to calculate joint probability function for discrete variables, how to derive marginal probability function for discrete and continuous variables. For this lesson, for more information on this lesson, you can visit the web page of Netuno MedNetU project.